Okay, it seems to be thawed out enough for it to be rubbed in, so it's back to consistency. So we're just going to rub it in best we can without burning ourselves or anything. But my hands are pretty tough, you know, because I do usually have to put my hands under a hot tap on a daily basis these days, get rid of encroaching arthritis and things like that. So we'll see. Now I might need that bottle again. Where is that bottle gone? It's over there. We might even make use of this. Yeah. Always use a tool, Richard. Use a tool. So it is the original container, so as long as we don't break it, might better wash it out and use it again. So what do you think, fellas? Do you think 2 parts poly and that, or do you think we need 3 parts poly for this? Doesn't quite, because we added that, it takes that extra water, you see, probably compared to peat. I don't know, we'll see how it goes. Oh well, that bit hasn't gone in there. I think we've got enough of the heat. Once we go around and get enough of the heat out of it, we can then get the hands in it. So going around like this, I'm actually getting rid of some of the heat. You can actually feel it going out into the air, surrounding air sort of thing. I mean, if you want to cool something down really quickly, float it in a bath of water. If you float it, it cools down much more rapidly than just sitting it in there. So I think because it makes use of 2 modes of cooling. I keep getting them confused, but you want to look them up. They're well known. Is it convection and what's the other one? I think it's making it cools down more rapidly because it's making use of 2 modes of cooling or transfer of heat energy. Okay, so I think that's most of the done there. So you think there's a lot of air trapped in there, and eventually we might totally occlude all the air in there and fill it up with reductive oh, the other thing I wanted to talk about, yes, hang on. Yeah. Yes, this is the this. I know what I can do. Let me just wash this container out. I'll just make use of these. While the tap, it would be better. Much more succinct. But yeah, this is our nickel one that totally got rid of all the ammonia stuff. If we pour some of this in here and then add our magnetic indicator here, if we do this, you'll get a surprise. It's acid, pH, green, pH of 4. Yeah, it's the universal indicator, the true one, you know. Red is 1, orange is 2, yellow is 3, which is the colour of peat. Peat's supposed to be around about 3, check it with that, so, you know, it ties in with peat, you know, so, you know, don't poo-poo it until it still actually starts matching the things you know. And 4 is, green is 4, grey is neutral, of course, because there's a combination of dyes that give that sort of grey look, and there's very few things that give you a neutral thing. Paraffin wax and polystyrene are 2, the only ones I know of, really, and maybe there are others, but this, though, a mixture of the nickel and the copper. You can still smell, well, there's no smell of it, but it's still got the ammonia smell in it. So it's still got this ammonia smell. If we put some in here, yes, there you go. Look at that. It's alkaline. So, so what does that mean? Does that mean that the nickel is not strong enough to pull the ammonia away from the copper? Or is the modus operandi of the nickel, does it absorb the hydrogen? Because they know that nickel metal can absorb hydrogen. Maybe the nickel atom itself could actually interact with reductive flammable gas sort of thing? Does it pull the hydrogens off the ammonia, therefore releasing the nitrogen as some form of nitrogen gas? Do you see little... Have we not noticed over the 2 or 3 week period that every day there's little tiny bubbles going up? Maybe they're so microfine we don't actually get to see them, you need a microscope. But what about this precipitate there? Does it mean it's actually locking down the reductive flammable gas in some form? You know, but there's so little nickel in here. And there's so much ammonia, because ammonia is so soluble. It's a 1 in 80 fold. In other words, you can get 80 cubic centimetres in 1 cubic centimetre of water. In other words, 1 litre of this can hold 80 litres of ammonia gas. And we know that 22.4 litres of a gas is a mole, so that means it's about not quite, it's slightly under 4 moles, so it's between 3 and 4 moles of ammonia in a, you can get 3 or 4 molar solution of ammonia in a 1 litre container, basically. If Avogadro's number and the PV equals nRT rule still holds, well, you can do that. But anyway, enough said. Things are getting rather interesting, and I think we're going to be ruling out sand, fellas, which is very strange in the sandiest continent, probably the saltiest continent, one with the big slabs of serpentine, nickel. Maybe we got degraded silicate in this country. We're so old that our silicate doesn't do the things that other silicates do. But then again, I am doing my dough on bags of sand which are mined here, so 6, 1.5 dozen. Maybe the sand in WA is different to the sand in other parts. Maybe the sand is in the Northern Territory and in WA are different to the sand in the rest of the parts of the country. I don't know, but maybe being so close to the big areas of serpentine, maybe the nickel has an effect on the silicate. I don't know. Maybe it prevents this sort of storing of the reductive flammable gas. I don't know. Does it have some sort of also effect on the copper? Because as I said in the past, I've had my biggest scientific explosion coming out of copper, which is very strange. So anyway, we'll see if we can make some progress. I'll pot this up in a standard pot, and we'll go from there. And if we get pinking or redding in 4 days, well,